and welcome. On this video, I'd like us to talk about matrix transpose and the traces. Okay, so let's start off with the transpose. So let's suppose you have a matrix A where the matrix A has an order of n by m. So remember that the order is given by row times column. So in this case, n represent the number of rows and m represent the number of columns. Okay, so now the transpose of matrix A is going to be denoted by a to the power t, like that. So how do we find the transpose of matrix A? When you're finding a transpose, basically what is happening is that the rows becomes the column and the columns become the row. So by that I mean now is the order of matrix the transpose of matrix A is going to be m by n. It's going to be m by n. So if it is m by n, we see that, oh, for A, m was the number of columns, but now for the transpose, those columns became the rows, and then n was the number of rows. Now the rows became the column. Okay, so let's dive into an example and see what this basically means. So if you have a matrix A with entries 1, -2, 3, 4, like that. So the transpose of matrix A, we say that the rows are going to become columns. Okay, so we see that we have a row. This is row 1 and this is row 2. Okay, so we're going to take the rows and make them columns. Remember, columns are vertical, so that row of 1 and -2 is going to become a column for the transpose of matrix A. Then the second row is also going to be turned into a column. So this is the transpose of matrix A, just like that. So since A is a square matrix, the other way of finding the transpose only for square matrix, we know that A is a square matrix. So what I'm about to do only applies when we are dealing with square matrices. Okay, so the other way we can go about it is that we can say, if we want to find the transpose, we keep the diagonal as it is. We do not change the diagonal. Okay, so the diagonal is 1, 4, like that. Then we swap the corresponding entries, like in a diagonal, like that. We swap them. So basically, we are going to swap -2 with 3, like that. So when we first did it according to the definition, we saw that the diagonal remained the same. Then what changed is the entry, this one, is now there, and then the 3 that was on the bottom entry there is now up there. Okay, so basically that is what I'm saying. If it is a square matrix, you can keep the diagonal as it is and swap the corresponding entries on a diagonal, like that. Okay, so you keep this diagonal as it is. Okay, so let's look at another example. Let's suppose you have a matrix B, where matrix B has entries 7, 2, 1, then 3, -1, and 4, like that. Okay, let's add one more, 0 and -2. So if we want to find the transpose of matrix B, the transpose of matrix B is basically going to be what? The row becomes the column. So it's going to be 7, 2, 1, 0, like that. And then this row also becomes the column. So it's 3, -1, 4, -2, like that. Okay, so remember the fact that we made here about keeping the diagonal like that. So we see that matrix B is not a square matrix, so it has no diagonal. So we cannot just simply say there is something that we keep like that and exchange other entries. Okay, so this is what I meant, that it only applies to a square matrix. Okay, so now how about the inverse of a matrix? How do we go about finding the transpose of an inverse of a matrix? So if we are having matrix A with entries A, B, C, D, like that, the inverse of matrix A is basically going to be 1 all over the determinant of matrix A multiplied by these two. They are going to swap. So you have D, A, like that, and then these two, they're going to have negative signs, -C, -B, like that. Okay, so the inverse of a matrix for a 2 by 2 matrix, this is how you find the inverse. Okay, so if A, for example, was negative 1, 4, 3, 1, like that, was negative 1, 4, 3, 1. So the first thing that we want to find is the determinant for in order for us to find the inverse. So the inverse was going to be 1 all over. The determinant is basically negative 1 by 4. That is negative 4, then minus 3. Okay, so we see that the determinant was going to be 1 is going to be minus 7. Then what do? We exchange D. We exchange A and D. So in this case, our A is negative 1 and our D is 4. So we're going to have a 4 there and a negative 1 there. Then the other thing that we do, we put negatives on CD. So our C is this one. So we're going to have negative 3 and our D negative 1, like that on our B. Okay. Then now we can simplify. This becomes 1 all over minus 7 into 4 minus 1 minus 3 minus 1, like that. Then we can multiply by the determinant inside there. Then we get minus 4 over 7, 1 over 7, 3 over 7, then 1 over 7 again, like that. So the inverse of A is this one. So now how about the transpose of that? So if we're looking for the transpose of that, it's basically something like this. Okay, so the transpose of the inverse of A is going to be what? We said that the rows becomes colon, so it's minus 4 over 7, then 1 over 7, like that. Then this row becomes colon, it's 3 over 7, and 1 all over 7, just like that. Okay, so this is basically how you go about it. Okay, so suppose before on this very same example, before we found the inverse, we just said let's find the transpose. Okay, so I'm just going to look for the transpose of this matrix. So the transpose of that matrix is basically, we're going to keep the diagonal as it is. So I'm trying to get you into the jinx of using multiple techniques, so that if you forget the other one, then you can use the one that you remember. Okay, so since it's a square matrix, we're going to keep the diagonal as it is. We said minus 1, 4, like that. Then we swap 1 and 3. So basically here is going to be 1, then there is going to be 3. Okay, and now after we have this, they tell us that they want the inverse of that transpose. So the inverse of that transpose will be denoted by something like this. Okay, so if they want the inverse of that, we know it has to be 1 all over the determinant according to this formula we were using here. It has to be 1 all over the determinant. The determinant is going to be minus 1 by 4. So that is minus 4, then 1 by 3, then minus 3, like that. Okay, then it tells us that these two have to swap. These two, they have to swap. Then we have 4 and minus 1 there. Then these two, they must have a negative sign. Then minus 1, minus 3. Just like that. Okay. So here we're going to get minus 1 all over 7 into 4 minus 3 minus 1 minus 1. Just like that. Okay. Then now, this is going to be simplified to minus 4 over 7, then 3 over 7, and here 1 over 7 and 1 over 7, just like that. Okay, so notice something. This is a bit messy, but then now this one is basically the inverse of a transpose. Yeah, notice something about the inverse of the transpose. On this one, we started by wanting the inverse first. We got the inverse to be that. Then we wanted the transpose. Okay, the transpose of the inverse matrix. Right? We got this. And for this one, we first wanted the transpose. After wanting the transpose, we wanted the inverse. Then we found the inverse to be that. So what do you notice about this actually? What do you notice? Notice that the transpose of an inverse, let me write that down. The transpose of an inverse is basically the same as the inverse of a transpose for a square matrix, for a 2 by 2 square matrix. So we can try another example and see if ever this holds for all matrices. Okay, so we say that the inverse of the transpose of an inverse is equal to the inverse of a transpose. Okay, I'm just gonna write that down again here so we can remember what we said. We say if you have the transpose of an inverse, it must basically be the same as the inverse of a transpose, like that. Okay, so now let us use a different matrix and see if that is true. Let's say we have a matrix with entries 1, 6, 2, -1, like that. Okay, so the first thing that we want is to find the inverse. We are working from the left hand side. We want to find the inverse, then transpose it. Okay, so the inverse of matrix B is going to be 1 all over the determinant. So the determinant is 1 by 6 minus 2 by -1. So that is basically plus 2. Then we exchange these 2, 6, 1. Then we put negatives on those 2. So -2 and 1, like that. Okay, so this simplifies to 1 all over 8. The entry 6, 1 minus 2, 1, like that. Then 1 over 8 by 6, that basically gives us 3 over 4. 1 over 8 by 1 is 1 over 8. Then 1 over 8 by -2, that is basically minus 1 over 4. 1 over 8 by 1 is 1 over 8. Okay, so this is the inverse. Now we want the transpose of the inverse. The transpose of the inverse. So the transpose of that inverse, this row is going to become a column. So it's 3 over 4 and 1 over 8, like that. Okay, then this row is also going to become a column there, minus 1 over 4 and 1 over 8. So now we want to find this and check if ever it's going to give us the same matrix that we got here. So if that is the case, then we know that this statement holds, it's true. Okay, so the first thing from the right hand side, we see that we have to first find the transpose. So the transpose of matrix B is basically we change this to be a column. So my 1, sorry about that. So it's 1 and -1, then 2 and 6, like that. Okay, then now we have found the transpose. We want the inverse. So the inverse is basically going to be 1 all over 8. So you realize the determinant is not going to change. Okay, because it's 1 by 6, that is 6, then 2 by -1, 6 minus -2, then that is going to be 1 over 8, like that. So these two, they are going to change. We have 6, 1. These two are going to get negatives. So here we're going to have 1 and there -2. Okay, so basically distribute 1 over 8. Here, whether we're going to get 3 over 4. Okay, then that by that, get minus 1 over 4. Then 1 over 8. And 1 over 8. Just like that. So we see that this is basically what I forgot to write it here. This is the inverse. This is the inverse of the transpose of matrix B. So we see that the inverse, the transpose of the inverse of matrix B is this. and also the transpose of matrix B, the inverse of it, is that. So we see that, this statement holds for as long as you have a 2 by 2 matrix. So this is always the case. Okay, so now let's move on to traces. If you fell behind while I was explaining the transpose, feel free to rewind the video and check what is basically going on. Okay, or let me just do one last example on transpose before we move on. Let's suppose you have a matrix C. Now with let's make it a 3 by 3. Let's say you have 1 there, minus 1, 3, 0, 4, 2, 9, 1, 10. Okay, so I'm gonna do it two ways quickly, where I'm applying the definition that the rows are gonna become the columns, and also that one of keeping the diagonal as it is and exchanging the corresponding entries. Okay, so the transpose of C, by definition, this row has to change to a column, so it's 1, minus 1, 3. Then this row change to a column, 0, 4, 2. Then this last row change to a column, so 9, 1, 10, like that. Okay, and using where we keep the diagonal, it's basically going to be, the diagonal is 1, 4, 10. Okay, so 1, 4, 10, like that. So we're going to exchange -1 with 0, and exchange 3 with 9, then exchange 1 with 2. Okay, so where there was -1, we're gonna put 0, and where there was 0, we're gonna put -1, like that. Okay, then where there was 9, we're gonna put 3, and where there was 3, we're gonna put 9. So there is 3, and then we're gonna put 9. Okay, and now where there was 2, we're gonna put 1, and where there was 1, we're gonna put 2. So we put 2 there, then 1 there. So notice that these two matrices, that these two transpose are the same. It's just two different approach, where this one I'm just keeping the diagonal, and this one I'm using the definition. So now let's move on to traces. So what are traces? Basically, traces is the summation of the diagonal. Okay, so if we have a matrix A with entries A, B, C, D, E, F, G, H, I, like that. So the traces is basically the sum of the diagonal, and it's denoted by TR of A. Okay, TR of A is basically going to be A plus E plus I. Let me just use a small letter there. Yeah, like that. Okay, so it's basically the sum of the diagonal. We are summing the diagonal in order for us to find the traces of a matrix. And notice that a trace is undefined if it's not a square matrix. If we are not dealing with a square matrix, then the trace is undefined. So what I mean by not something is not a square matrix, let's suppose we have a matrix B with entries 1, 2, 3, 1, 0, 1. So if the number of rows and the number of columns are not equal, then we know that this is not a square matrix. So we see that this is actually 2 by 3. We have 2 rows and 3 columns. So this is not a square matrix. So it doesn't have a trace. Since we see that we do not have a diagonal, we cannot say 1, 0 is our diagonal, because we see that, also 3 and 1, they go the same way that 1, 0 goes. So basically we do not have a diagonal. So that's why the trace of matrix B, it does not exist, so it's undefined. Okay, so let's dive into it and see practical examples. Let's suppose you have a matrix A. Remember, they always have to be square matrix. So let's say we have 2 minus 1, 0, 8. So basically the trace of matrix A is going to be 2 plus 8, which gives us 10, like that. Okay, so yeah, traces are actually straightforward. So for as long as you have a square matrix, you just take the sum of the diagonal. Okay, let's see if we had another matrix C with entries 1, 0, 3, -2, -7, -1, 3, 4, 9, like that. So the trace of matrix C was basically going to be 1 minus 7 plus 9. So that is going to be 3. Okay, so feel free also on the traces to go back and make sure you understand what we have been doing, and also do not forget to hit that notification bell and the subscribe button so that you're notified next time I drop. Thank you very much and all the best.